For Josh Goldberger, this site never gets old. This is a crystal growing inside what's called a floating zone furnace. Give it a few hours to run, and the end result is a single, nearly flawless crystal, as big as a pencil.
My group is really interested in creating new families of materials, and particularly electronic materials.
Goldberger's creation is a crystal of what's called rhenium silicide. It may look pretty modest now, but crystals like this may one day rewrite the book on how electronics operate.
So we're looking into lots of different applications for this new discovery, this new family of materials, and electronics is one of them. There's a 30-year valley from discovery till actual commercialization. We're on year one.
It all starts here at the Bulk Crystal Growth Facility at Johns Hopkins University. It's part of a larger materials innovation platform called PARADIM, funded by the National Science Foundation. They're working to make groundbreaking advances in material science.
We are the only location in the United States that has all of these crystal growth methods, the most unique and up-to-date crystal growth methods, and it's open to users like Josh.
A lot of these crystals, they're not necessarily like we learned to do in science class, where we grow rock candy or we evaporate water to grow salt single crystals. A lot of these materials have very high melting points or very high vapor pressures.
Rhenium silicide has an incredibly high melting point. In order to grow a crystal of it, we need to get to 3,600 degrees Fahrenheit. That's hot enough to melt bricks.
They need big, pure crystals in order to study what have turned out to be intriguing quantum properties.
There's a lot of different ideas behind what makes a material a quantum material. It's a very broad idea. Our project is all about electrons. I view a quantum material as a material in which electrons move in mysterious ways.
Today's electronic materials are largely silicon-based. Sprinkle in what are called impurities, like boron and phosphorus, and electricity can start flowing. Depending on which impurities you use, the current will be either positively or negatively charged, forcing it to flow in one direction. A device, like say a smartphone, has a complicated mashup of many of these electronic components that are carefully configured to work together. But what if one material could do it all with much faster performance?
We found a new kind of electronic material in which negative charge travels one way through a material and positive charge travels simultaneously through a different direction through the crystal.
This quantum behavior was so new, it didn't even have a name.
We came up with this word to call this. We call it goniopolar materials. It comes from the Greek prefix gonio, meaning angle, and polar, meaning a conduction polarity, negative charge or positive charge.
Lots of testing goes into making sure the crystals are pure and that they understand their structure and performance. And they're figuring out how to engineer these quantum properties into other materials. Rhenium is pretty rare.
At best, there's maybe a couple of tons that are mined every year, and so that is nothing compared to silicon, which you can just get from sand on the beach, for instance, right?
But other goniopolar materials made of more common elements could one day make sense for industrial scale use.
When I started this research, I used to think that we were looking for a needle in a haystack. And now that we've made a couple of new goniopolar materials, now I realize that we're not looking for a needle in a haystack. We're looking for like a bright red pincushion full of needles inside a haystack.
Designing new crystals with unique quantum properties, paving the way for breakthroughs in electronics. For Science Nation, I'm Miles O'Brien.